Thank you very much for this invitation, for that introduction. It seems like a wonderful conference, and I hope there are many more. So let me start with the title of this talk. It's about to reach its expiration date. I've been using it for about a year, but it seems to elicit interesting responses from people who don't know what the talk is about. So let me justify the choice of title, the general case, and notice there are quotes around here, and that's because this is a quote from actually several sources, early sources in the early development of the ergodic theory of dynamical systems. So, whence the general case? This is a quote from a paper that appeared in the Annals of Math in 1941. In it was proved a famous theorem by Oxybutynin and Ulam called the Oxybutynin Theorem now. And the quote reads, "The conjecture has frequently been expressed, first by Birkhoff, then by Hopf, that's his Eberhard Hopf, and others, that ergodicity is probably the general case. The conjecture was never given a precise formulation, but was based on the idea that a general transformation or flow should be expected to shuffle points in a more or less random fashion, and therefore leave invariant as few sets as possible." So if we accept, or if we take as a definition, a very preliminary definition of ergodicity of a dynamical system, that the dynamical system, which is a transformation of a space that you can iterate, does not preserve any structures other than those that are negligible from the point of view of probability, and I'll say this on the next slide, then what Oxybutynin and Ulam are referring to is a kind of a mindset that was around in the 1930s, that dynamical systems, or at least those that were encountered in natural applications, should not have any strange invariant structures, or at least they should be expected not to have any of these invariant structures. They should be expected to be ergodic. I'll return to this quote, but let me give you a precise definition of ergodicity. So we start with the probability space. Hidden in this notation is a sigma algebra. In the applications I'm going to discuss today, X is going to be a compact manifold and mu is going to be the natural volume on the manifold. And we will consider a transformation of this space, that's just a function from the space to itself, that preserves the measure. So that just means that if I take the push forward of mu, I get mu. Or equivalently, if I take a set A that's measurable, and I look at its pre-image, it will have the same measure as A. Okay, so this is called a measure-preserving dynamical system, and such systems can be iterated, and they continue to preserve measure. And such systems can be examined from a probabilistic viewpoint. And so we can look for invariant functions, invariant sets, and so on. Ergodicity is the most basic minimality condition that one could impose on such a system. And so the definition of ergodicity, the sort of simplest definition one could give, is that if I have a set that's invariant under F, then it's trivial from the point of view of the measure. It has measure, probability, if you like, either 0 or 1. The remarkable thing about this definition is that it came quite a bit after the notion, the kind of popular notion of ergodicity already existed. The notion of ergodicity goes back to Boltzmann's study of ideal gases, and the way Boltzmann formulated ergodicity was rather imprecise, but what it said was the following. So this is a formal version of ergodicity a la Boltzmann. And it's equivalent to this definition, but that's by a theorem. So what's the equivalent formulation? It says that if I take any function or measurement on this set X, integrable, and I average it along iterates of F, then almost surely this average will converge to a constant, this constant being the average value of the measurement phi. So for example, if X consisted of the ensemble of all possible states of an ideal gas, and phi is the temperature of a given ensemble, then ergodicity would say that if I start in almost any state of the system and I let time evolve and I measure the temperature over time and I average it, it will converge to some canonical number, which is the temperature of this system. So this equivalent statement is a deep theorem due to Birkhoff in 1931, called the Birkhoff pointwise ergodic theorem. And colloquially, the statement is known as time average, so this is averaging over iterates of the system, equals space average, and this is averaging over the set of all possible states of the system. Here's another equivalent statement. So we have this dynamical system, and we say, or it is ergodic, if for every measurable set A, and for almost any point x, if we do the following, we start at x, the point in the system, we apply f, which we can think of as letting time evolve 1 unit, and we measure whether f is in A or not, and we apply again, and we measure whether f is in A or not, and we count the number of times that point x visits A. And then with probability 1, this will converge to the measure of A, the proportion of x that is occupied by A. So another way of saying this is to say that almost every orbit, that is the orbit of almost every point with respect to mu, is equidistributed. It sees the measure mu. The orbits visit sets proportional to their measure. Okay. So here's some examples of measure-preserving dynamical systems. The most basic and sort of simplest one, non-trivial one that's not finite, takes place on the unit circle, which is the additive group, R mod Z. What's the transformation? I take the circle, which is circle of unit circumference in this representation, and I rotate it through an argument alpha, or 2 pi alpha, if you like. Well, the definition of the Lebesgue-Haar measure, it is the unique measure that's invariant under all such rotations. So in particular, it's invariant under this given rotation f. And it's not hard to see, and this is an argument, you can show this using Fourier series, or if you like, or there are more geometric proofs of this fact available, that this transformation is ergodic if and only if alpha is not rational. Okay. And the first proof of this was due to Weil. He proved several equidistribution results along this line. So here's just an illustration of this equidistribution, this ergodicity. So here's the circle. Here's the subset A. I've chosen an interval. And I choose almost any point. In fact, in this setting, I can choose any point. It's a special kind of ergodic system. And I rotate it through angle alpha, or through distance length alpha. And here's a picture of the orbit of alpha evolving over time, and you can see it's quite clear that in this particular case, the orbit of alpha is filling up the circle quite nicely. And it's not a stretch to believe that the proportion of time spent in that interval approaches the length of that interval pretty quickly in this case. Now, by contrast, just to really illustrate this dichotomy, if alpha is rational, then, so here's a rational number. If I look at the orbit of a point under, any point under a rational rotation, it will be finite. It'll come back to where it started. In fact, if alpha is p over q, it'll come back after q iterates. And so in this particular case, the number of iterates that visit this interval is 0. And obviously, that's not the length of this interval. And you might say, well, we only require almost every point visit this interval with the correct proportion of time. But you can easily see that there's a whole open set of points that don't visit this interval with the right proportion of time. So this is clearly not ergodic. This is what I would call a very rigid system. There's this strong dichotomy between periodicity and ergodicity. In any case, this is one of the first known examples. So this type of example of rigid rotations on compact groups, these examples were known to Oxybutynin and Ulam back when they wrote their paper in 1941. This is an example of a much richer class of, it's not an example in fact, of a much richer class of systems known as Hamiltonian dynamical systems. These were the dynamical systems that Boltzmann was interested in, and these were the types of systems that Oxybutynin and Ulam were referring to really in the previous quote. So Hamiltonian systems are dynamical systems that arise from solving ordinary differential equations on symplectic manifolds. The simplest forms of, the simplest type of Hamiltonian system to write down is when you start with a symplectic manifold R2n with the standard symplectic form. And if you follow the definitions of what the Hamiltonian vector field is in this setting, it's the following. I start with a function h on the space. It represents some kind of total energy of the space in physical applications. And the Hamiltonian vector field derived from this Hamiltonian is given by this pair of differential equations. The time derivative of q, which is the space coordinate, is the partial of h with respect to the corresponding momentum coordinate. And the time derivative of the momentum is minus the partial of h with respect to qi. And any solution to this system of equations is going to preserve this energy by the way it's been constructed. So these equations define a flow, which is a continuous time dynamical system. And it preserves, since it preserves this function h, if I restrict to a level set, I get an induced dynamical system, and here I can see compact level sets. And it preserves the restriction of the volume to these level sets, known as the Liouville measure. So this is Liouville's theorem. And Hamiltonian systems provide a rich class of dynamical systems of physical interest. And they preserve volume, and if I normalize this volume to be a probability measure, I can ask whether such a system, when restricted to a compact level set, is ergodic. And it was these systems that one guessed that the general case would say were ergodic. So some examples of Hamiltonian systems. This is just a brief kind of survey here. And so I've drawn some pictures to illustrate Hamiltonian dynamical systems can have a wide variety of behaviors. So for example, here's the hot flow on the 3-sphere. That's a Hamiltonian system. For a very simple Hamiltonian, you can write down on R4. And here, all the orbits of the flow are closed. And it's not hard to see this is clearly not an ergodic system. Here is a schematic of the circular restricted 3-body problem, which was studied by Poincaré back in his award-winning paper in 1872. This is this celestial mechanical system, as all other planetary systems are, is also a Hamiltonian system on, a reasonably high-dimensional phase space that goes up, pretty fast when you have a lot of planets in 3 dimensions. And so the prediction of the future behavior of a given configuration of planets with a given configuration of momenta, that's a problem that belongs to Hamiltonian dynamical systems. This here is a picture of a schematic for the ideal gas problem studied by Boltzmann. So this can be formulated actually as a billiard problem. If you put this in on a torus or in a box, This is studying the configurations of molecules, ideal gases, where the molecules bounce off of each other without any loss of energy, and the temperature in the system is maintained at a constant. So the question about how the configurations of this system is another question that belongs to Hamiltonian systems. And these sort of lie across the spectrum, in fact. So this is really a rather rigid system, whereas here we see an interesting mix in these types of systems between rigid and very chaotic behavior. And this tends to be a highly chaotic system, and this is the type of system that Boltzmann was originally interested in, where he formulated his ergodic hypothesis. So this is a crude approximation of what was the landscape circa 1940, which is when Oxybutynin and Ulam were graduate fellows at Harvard studying ergodic theory in the same place where Birkhoff was. As I said, Boltzmann had formulated an ergodic hypothesis for ideal gases, which roughly said that the typical dynamical system should typically be ergodic. Weil, on the other hand, had studied in the early part of the 20th century, had studied equidistribution for rigid systems, including the four rotations that I described before. Poincare and Birkhoff were very interested in the systems that arise from celestial mechanics. They were not addressing exclusively questions of ergodic theory. There were also interesting questions concerning chaos that were not an almost everywhere question, but much more specific. But what they had discovered already at this point was some very interesting chaotic behavior in these celestial mechanical systems. So these are pictures in this circular restricted three-body problem where there's a sun and moon and then like a little satellite, and you can see the satellite behaving quite chaotically with respect to these other two planets. These are actual trajectories. Okay. And then finally, and this work is some of the most important work with respect to what I'm about to say. So this is work of Hopf and Hedlund. What they were interested in were geometric systems. So there were no physical, these were not really physics systems. They studied the geometry of negatively curved manifolds, in particular a compact surface of negative curvature. And they were interested in the distribution of geodesics in these surfaces and higher dimensional manifolds as well. And they addressed the very simple question, if I take such a surface and I pick a geodesic at random, how is it going to fill up the surface? Is it going to be dense? Even a more interesting question, is it going to fill up the surface in an equidistributed way, or even fill up the directions on the surface in an equidistributed way? And what Hopf proved in a very influential and important paper was that there's a mechanism, and it's a very robust mechanism, that creates ergodicity in an associated dynamical system called the geodesic flow for these surfaces. So this was the landscape, and at this point these were basically the known classes with a few kind of more artificially constructed examples, not on manifolds, but these were the known examples of ergodic dynamical systems around the time when Oxybutynin and Ulam were addressing this sort of general case. And in particular, a question that was unknown or open at that point was, is there some type of topological obstruction to ergodicity? Given a manifold with a volume on it, can you find an ergodic transformation of the manifold? And let's say it has some regularity, like a continuous ergodic transformation. That was open. And you can see why there was some question as to whether there might be some topological obstruction. Okay, so this is the background for the quote that I just gave you of Oxybutynin and Ulam. So let's return to it. So this paper that I've mentioned addressed this question and in fact solved this question, at least in an important initial context. So what did Oxybutynin and Ulam do? Well, they addressed the question, first of all, does every manifold admit an ergodic transformation, continuous homeomorphism. So what did they prove? They proved that every manifold supports such a homeomorphism. And how did they construct these homeomorphisms? Okay, here's a pun that I've made now twice, and it's also reaching its expiration date, but I kind of like it. So if you want to construct an object in mathematics in the topological category, there are a few ways to do it. One is to try to do it with your bare hands, and another is to try to do it with your bare hands, with a capital B, i.e. bare category theorem. So the space of homeomorphisms of M, preserving orientation, preserving of M, preserving volume, is a bare space, meaning that any countable intersection of open and dense sets is dense. And such an intersection, a dense G delta, is known as a residual set. And if a property holds for a residual subset of homeo M, we say it's generic in that bare space. And so what they proved is not only does there exist such a homeomorphism, but there are lots of them, at least in this topological sense. And bare sets are large, dense G deltas, residual sets, are large in at least some senses. For example, the intersection of two such generic sets are residual sets is residual, so you can't have two disjoint residual sets. In the example of the circle, we can actually see that this theorem is true in a rather trivial way from what I've already said. Because if M is the circle and volume is length, the orientation preserving homeomorphisms of the circle are precisely the rotations. And so the topology on these rotations induce the uniform topology coincides with the topology on the real line given by alpha, right? And so if alpha is rational, then we're not ergodic. But if alpha is irrational, and this is an example of a residual set, then it's ergodic. So in some sense, what Oxybutynin and Ulam did was to in some actually rather strong sense, what they did was to generalize this result about circles to homeomorphisms of manifolds. And so in some sense, we've answered this question, or they answered this question, so I've now stated it more formally. Every compact manifold, I've already stated it, but now I've got a picture. So here's the schematic, this purple set representing the bare space of homeomorphisms of M in the uniform topology. And then I've represented the ergodic maps, this residual subset, by this very dense looking subset. Okay. So this is the Oxybutynin theorem, and it's just the beginning of studying this question of whether ergodicity might be a typical property among dynamical systems, in particular the one studied by Boltzmann. There's a caveat to the Oxybutynin result, and a caveat was recognized, stated by Oxybutynin themselves. So I will read the quote. It must be emphasized, however, that our investigation is on the topological level. The flows we construct are continuous groups of measure-preserving automorphisms, but not necessarily differentiable or derivable from differential equations. Thus, they correspond to dynamical systems only in a generalized sense. In particular, these Hamiltonian systems, which are quite differentiable, are probably not at all seen, and in fact aren't seen in this set that Oxybutynin and Ulam construct, at least not on most manifolds. So let me kind of give you an idea of how the Oxybutynin-Ulam proof works, and maybe this will give you an idea for why this theorem of Oxybutynin-Ulam does not answer the question of whether the typical smooth dynamical system is ergodic. So here's a representation of a manifold. It's a cube, and in fact, because we don't care about zero sets, we can basically represent all manifolds this way. And that's what they did. We break it up into smaller cubes, and then what Oxybutynin and Ulam proved is that if I have any homeomorphism, so it's going to it's going to take these cubes, it's going to move them around. It's obviously not going to take cubes to cubes, a typical homeomorphism. But what they showed is that it can uniformly be approximated, if the cubes are small enough, by a homeomorphism that does basically this. Throws all the cubes out and rearranges them. So it's just a permutation of little cubes inside of a big cube. And if you think about it, a permutation of cubes is very much like a rotation on a circle. So what Oxby and Ulam proved is that by this kind of very simple combinatorial, like you can do it with a marriage lemma argument, a volume-preserving homeomorphism can be approximated very well, sort of arbitrarily well, by this non-continuous but almost continuous transformation that is easily perturbed to be ergodic in the measurable category. And then using some kind of Lucen type arguments, one can then show that this implies that ergodicity is a dense property among homeomorphisms, and then ergodicity is a G delta. So once a property is dense, if it's a G delta, it's a dense G delta. Okay, so it's residual. Okay. So why doesn't this work for smooth systems? Why, in other words, why can't I approximate a diffeomorphism in a C1 sense, if that makes any sense, locally, some kind of C1 sense, by a permutation like this? Well, because it just doesn't work, okay? And if we're in a high enough smoothness category, the Oxybutynin theorem fails. So here's a quote, again, talking about the general case, from Kolmogorov's ICM talk in 1954. It's a translation. So let me read this. Are dynamical systems on compact manifolds, generally speaking, transitive? Transitive means ergodic in his language. And should we consider a continuous spectrum as the general case? So continuous spectrum is something stronger than ergodicity. And a discrete spectrum as the exceptional case. So this is a kind of a little stronger than ergodicity, but basically like a rotation. Okay. In the application to analytic canonical systems, the answer to both questions is negative. So what does Kolmogorov mean by canonical systems here? He means Hamiltonian systems with an analytic potential, or with an analytic Hamiltonian energy function. And what Kolmogorov showed is for certain systems, Hamiltonian systems, such as the ones that arise in celestial mechanics, if you start with this system, and then, well, you don't really have a bare space of analytic systems, but you can still look at any finite dimensional perturbation of such a system by perturbing the Hamiltonian. You can find systems where no matter how you perturb the Hamiltonian in an analytic setting, it will not be ergodic. So there's no way that for these systems you could say that ergodicity is the general case. So these are analytic, they're highly differentiable. Well, this high differentiability can be reduced to finite differentiability, depending on the dimension of the manifold. So in particular, on a surface, the Kolmogorov, so subsequent work of Arnold and Moser, shows that ergodicity is not a dense property among the C3 area-preserving diffeomorphisms of a closed surface. So this is known as KAM theory, celebrated KAM theory. What's the mechanism for non-ergodicity? If I have a fixed point or periodic point for such a system, a Hamiltonian system, so really it's a flow, so it's a closed orbit, but then we can sort of take a section and look at the sort of transformation induced there. And suppose I have a fixed point or a periodic point more generally, and suppose the derivative, it preserves area, suppose the derivative is a orthogonal matrix, so some kind of rotation. And suppose further that around this fixed point, there's a normal form for the system, which involves a lot of twisting. So I won't say this formally, but it's a C3 condition. So it's preserved under C3 perturbations of a system, that is, systems that are uniformly small, the derivative is close, the second derivative is close, and the third derivatives are close. If you have such a periodic point, then there's a really good sized invariant set. In particular, we can find lots of circles enclosing this periodic point that are invariant. So here's a picture. This is for a very simple, easy to write down dynamical system. It's called the standard map. And here's an example of an elliptic fixed point. So this is just a perturbation of a Dane twist, 1, 0, 1, the linear map on the torus. This map has an elliptic periodic point with the twist condition, and you see these circles, these are invariant, and they separate the manifold into two invariant sets, a positive volume. So it's not ergodic, and if I perturb the system, it remains not ergodic. So here's another schematic. If we look in the space to be safe, let's say C infinity, if we look in the space of C infinity diffeomorphisms, now this is true in any dimension, in fact, I can always find in any manifold a non-empty subset consisting of these so-called KAM systems that are not ergodic. So there's no way you could have a dense set of ergodic systems inside of here. Now, one question that interests me very much is what happens outside of here. And I could actually tell you quite a bit. And the South Americans, and well, more generally Latin Americans among us, have done a lot of work to say what's going on here, as have I. But that's not the subject of this talk. Okay, so I'm not going to talk about C infinity systems, although it's extremely interesting and very hard as a general question. What I'm going to talk about today is, well, Oxybutynin and Ulam considered continuous systems, homeomorphisms. What about C1 systems? In particular, what if I look at the space of diffeomorphisms of a compact manifold, preserving volume, in the C1 topology? So I allow myself, I say that two systems are close if they are uniformly close and their derivatives are close. And I want to ask, well, in this setting, where we have C1, it's not C3, and it's not C0, what happens, right? Is there some transition between the KAM and the Oxybutynin? Well, KAM definitely fails in this setting, so that you can show. And Oxybutynin fails with any differentiability, so in the C1 setting, there's no Oxybutynin theorem. And let me explain why as sort of a meta. The technique, I should say. There's no Oxybutynin technique. What do I mean by technique? I mean, can you approximate a system in the C1 topology by one that permutes cubes? So one that looks kind of like a rotation. That fails. Why? I'll say in the next slide, I guess. Okay, so the question, by the way, that I've just posed about what about C1 and C2 is open. It's completely open. But I'm going to give a, I think, rather satisfying partial answer to this question in the C1 setting. So I think there's a strong argument to be made that C2 is probably quite different than C1. Okay, so why do I say that the Oxybutynin technique fails with any differentiability? That's because there's really an obstruction to this technique. Okay, so there's a number that I can assign to any dynamical system preserving volume called the entropy. And if this entropy is positive, you're not going to be able to do an Oxybutynin kind of trick. Okay, so what is positive entropy? Okay, well, what is zero entropy? Okay, so I'll tell you what zero entropy is, and then positive entropy is not zero. Okay, so roughly speaking, F has zero entropy with respect to volume. So this is an invertible volume preserving transformation. If and only if the growth and complexity of any partition under F iteration is sub-exponential. So let me say something rigorous, and then say something that's equivalent. So what do I mean by this? What I mean is, if F has zero entropy, then if I partition my manifold in any way I want into finite partition into positive volume sets. Okay, so these sets could be Cantor sets. This is just a cartoon here. I take any such partition and I apply my diffeomorphism to the partition. It will shuffle these elements of the partition around. And as I do this, I get a refined partition by intersecting. Okay, so here's a P1, which is a refinement of P and F of P. And I can continue to do this K times. Now, if I started with the identity map, which is quite clearly not ergodic, then these elements of the partition wouldn't change, right? So, in fact, P1, P2, P3 would all be the same partition. If my partition has a lot of expansion and motion and chaotic stuff going on, you would expect elements of this partition to get some of them to get extremely small very quickly. So, for example, if I took a circle and this is not invertible, but if I doubled it, and I took inverse images of partitions, and I took this sequence pk, what I would get, pk would be, if I started with partition into 2 pieces, pk would be a partition into 2 to the k plus 1 pieces, all of the same measure. And so the elements of this partition would go to 0 and measure very fast. Zero entropy says that, well, the elements of this partition can go to 0. In measure, it can't happen exponentially fast. So equivalently, if I take almost any point x and I look at the elements of the sequence of partition nesting down to x, then if the volume can go to 0, but sub-exponentially. So if it had gone to 0 exponentially, this would be negative. Let me give an equivalent way of saying this. If I fix a partition, and I think of pk as labeling trajectories of points, actually backwards trajectories of points, then what zero entropy says is if I know where a point is, which element of the partition it visits in the future, I know what point I'm at exactly, basically. So, or I shouldn't say know what point, but I know exactly what element of the partition I'm in at that moment in time. Okay, so that's entropy 0, and positive entropy is a complement, so it's a more complex type of dynamical systems. And here's a meta proposition that you can somewhat formalize. So if this Oxybutynin technique, approximation by periodic systems, holds inside a class of volume-preserving dynamical systems, then zero entropy is generic in that class. So if we could apply the Oxybutynin technique among C1 diffeomorphisms, then generically C1 diffeomorphisms would have entropy 0. Well, we can in fact apply this to homeomorphisms. So in fact, the generic homeomorphism has entropy 0. There's very low complexity, which should not be surprising because a rotation like this, for example, a rotation on the circle, has entropy 0. But that's not the case for diffeomorphisms. And here is an example. So, not on all manifolds, but on many manifolds, one can actually find open classes of positive entropy maps in the space of C1 volume-preserving diffeomorphisms. And so this technique fails. Oh, so I had some pictures. I had a good picture, which I probably should have put in here, and I didn't. The picture was of a system that has positive entropy. So let me describe it in words before I go on to the next slide. So let's take the torus, which is R2 mod Z2, and take a hyperbolic matrix. So that's just a matrix with integer entries that's invertible and whose eigenvalues do not lie in the unit circle. So an example is 2, 1, 1, 1. So that induces a map of the torus. That's a linear map of R2 preserving the integer lattice, and so it induces a volume and area preserving diffeomorphism of the torus. That map, because the eigenvalues of that map are not on the unit circle, there's expansion and contraction everywhere. There's no, there's quite, if I took a little cube and I apply such a map to it, it will stretch out quite a bit in one direction and get very thin in another direction. And this stretching out produces positive entropy. If I take a partition and I take a little cube and I apply the map, it's going to cross a lot of cubes. And since it's thin, it's going to slice those cubes. And since the width of an image of a partition element goes to 0 exponentially, shouldn't be surprising that the volume of these little cubes is going to go to 0 exponentially, area. And that's an example of an open class, a C1 open class of systems with positive entropy. Okay. So what is the main result I wanted to state is a C1 generic implication. So it says, okay, that's an obstruction, but it's the only obstruction. So in particular, so this is a joint result with Arthur Avila and Sylvain Corbusier, which is almost written. Actually, this part is written. There's another part that's almost written. So what does it say? It says C1 generically, positive entropy, this obstruction, actually implies ergodicity. It says something stronger. It says that if you have positive entropy generically, in a very strong sense, you look very much like this linear example 2, 1, 1, 1 I just described. So more technically, C1 generically, a diffeomorphism preserving volume with positive entropy is non-uniformly hyperbolic, and there's what's called a dominated splitting of the tangent bundle into stable Lyapunov directions and unstable Lyapunov directions. So it's what we would call non-uniformly Anosov. So here's another schematic, once again, just to describe this result. So inside of the space of C1 volume-preserving diffeomorphisms of M, we have an open subset that I referred to before, and we can characterize it. This is the set of diffeomorphisms with a dominated splitting. These are the systems that have stably positive entropy. These are precisely the systems with stably positive entropy. Outside of this subset, out here, we have a generic set of diffeomorphisms with vanishing entropy. Inside of here, we have ergodic, generically, ergodic and non-uniformly Anosov. So if we remove this obstruction of entropy 0, which is a low complexity condition and might lend itself to other methods, I'll say something later, in fact, a little bit of positive entropy, just one partition and one point or on one positive measure set of points where those partitions go to 0 exponentially fast, generically actually implies ergodicity. So here's the more, here's a different formulation of the same result. So if I have a generic volume-preserving diffeomorphism, that is, if I have a diffeomorphism belonging to a residual set, one of two properties holds. Either it has entropy 0, or it's non-uniformly Anosov and ergodic, for those of you who know that term. And I want to state some previous related results. The first, and this has a nice Latin American spin. So Ricardo Magnier was an Uruguayan mathematician who was at IMPA. In his 1983 ICM address, announced precisely this result for diffeomorphisms of surfaces. So the theme of this talk was to say, look, you can look at diffeomorphisms. On the one hand, they have smooth properties. On the other hand, they have measurable properties if they preserve area. And preserving area gives you a lot of measurable information. In particular, it gives you Lyapunov exponents, which are measurable quantities associated to such a system. It gives you an oscilladet split, again, a measurable splitting of the tangent bundle. And there's really not much more you can say for a diffeomorphism without further information. You have such a splitting. But what he said was, well, could we look at the smooth properties of the system and somehow bring together the C1, bring together the smooth properties with these measurable properties, at least in a generic setting, and say something stronger. He announced the result on surfaces that I stated before. So let me just volume-preserving diffeomorphism of a surface. Either it has entropy 0, so any partition has low complexity with respect to iteration and area, And now non-uniformly anosoph and ergodic actually gets replaced by anosoph. So the or is a very strong conclusion for surfaces. It says that I have a continuous splitting of the tangent bundle to the surface into two non-trivial subbundles. One bundle is expanded, the other is contracted. And for other reasons, we know that this has to actually be, after a continuous change of coordinates, a linear map like I described before. So what Magnier's result says for surfaces is that generically, either you have entropy 0 or you're a anosoph. In particular, you have to be on a torus. And there's topological reasons even that you can't have a non-vanishing line bundle. So one implication, which is interesting, says in the C1 topology, if I take the diffeomorphism of a sphere, for example, any diffeomorphism of a sphere preserving area, by a small perturbation, it has entropy 0. That's the C1 topology there. In particular, I could take one of these KAM examples, and by a C1 small perturbation, it has entropy 0. Now, that doesn't say that it's not ergodic, it doesn't say that it's not KAM, but it says that it's entropy 0, low complexity. So that was announced by Magnier. He died without having published this result, or having written down the details. He left an outline. And Jairo Bocchi completed this argument. It was a non-trivial thing to complete in his thesis work, which was published in 2002. So that explains this kind of strange dating system. And Bocchi and Bocchi-Viana subsequently generalized this result in several directions in higher dimensions and for symplectic systems. So it's a shame that Bocchi didn't make it here in time to introduce me, because he's probably done the most work in some sense on this and related problems, and we significantly use his work in a very significant way in several places in our result. In 2010, Hanna Rodriguez-Hertz, who's an Argentinian mathematician living in Uruguay, proved the case where the dimension of M is 3 in this result, using completely different methods, using methods for partially hyperbolic systems. And then I wanted to mention, just to point, it's a kind of a funny point. So there's a property that's closely related to ergodicity called transitivity, what we call transitivity. It used to be that the two terms were the same, usually called topological, or sometimes called topological transitivity. It asks that your system has at least one dense orbit. So an ergodic system, with respect to volume, certainly has a dense orbit, because an equidistributed orbit must be dense. In fact, almost every orbit is dense. The two conditions are far from the same, though, and it's easy to construct. Well, it's not entirely easy, but one can construct examples that are transitive but not ergodic. If we're just interested, though, in the property of transitivity, which is interesting in itself, Bonnetti and Corbusier in 2003 proved that in the C1 topology, if I take any volume-preserving diffeomorphism, generic, it will have a dense orbit. So if you could just go from transitivity to ergodicity, you'd have an Oxybutynin type result. But that, of course, remains open. So in my remaining minutes, I'll just say a couple things about the philosophy behind the proof. So as I mentioned, this work really builds on the work of quite a few people, and I haven't mentioned them all, but many of them being Latin Americans. So what's the philosophy, roughly? So there's systems called hyperbolic systems, uniformly hyperbolic systems. Examples of uniformly hyperbolic systems are the map 2111 that I mentioned before, these linear hyperbolic maps on tori. Another example are the systems studied by Eberhard Hav, the geodesic flow for a manifold of negative sectional curvature. That's a hyperbolic manifold. Another example, this is a singular hyperbolic system, is this idealized gas system, sometimes known as the Sinai Boltzmann billiard, This is not a smooth system. It's got some singularities, but away from the singularities, it's very strongly hyperbolic. These types of systems are ergodic, and this is due to the work of Hopf and Anosov and Sinai later in the 60s. It was generalized quite a bit. This is a very strong mechanism. You get ergodicity, but it requires a lot of hyperbolicity. It requires that everywhere you look in the manifold, you see expansion and contraction in transverse directions everywhere. Not almost everywhere, but so it requires a lot of strength, but then it gives you a very strong conclusion. It gives you ergodicity, and that's a robust mechanism. So hyperbolic systems, on the one hand, have positive entropy. That's why we have this obstruction to Oxybutynin. And they do tend to be ergodic. And I haven't really said why, but the mechanism for ergodicity is completely different than the Oxybutynin. So the Oxybutynin technique says approximate by something periodic. This Hopf technique, this Hopf-Anosov-Sinai technique says, well, I have a lot of expansion, and so if I try to average, or let's just say, I look at an invariant set for such a system, because if I iterate the set, it's going to tend to stretch out and be concentrated along these unstable directions. And if I iterate this invariant set backwards, it's going to tend to be concentrated along these stable directions. Okay. And the combination of concentration along stable and concentration along unstable actually implies, because these two directions fill up the manifold, it actually implies that the invariant set has to have full measure. That's just a caricature, but it's very different, right? It relies on the lack of periodicity of the system. Conversely, and this is, as I said, this is work of Bocchi and Avila Bocchi and Bocchi-Viana and others, systems with positive entropy have a tendency to have some kind of hyperbolic features. So they don't look like a geodesic flow for negative curvature everywhere. They don't look like the cat map 2111 everywhere, but there are positive measure sets in the manifold where you see this kind of invariant sets, where you see this kind of expansion and contraction. And, okay, this is the end of the caricature of the proof. The C1 topology. So where am I using the C1 topology? The C1 topology, remember, I can't change derivatives too much. I can't move points too much, but I'm free to do anything else I want. There's a lot of flexibility there. It's certainly not as flexible as the C0 topology, the uniform topology, but there's still enough flexibility left. It's gone once you get to C3, but C1 allows you to take a little bit of hyperbolicity and amplify it by small perturbations so that it's everywhere. And generically, that hyperbolicity is everywhere. And then you can use some of these techniques that go back to Eberhard Hopf to prove ergodicity and to prove that there's hyperbolicity in a very strong sense almost everywhere. So as I said, that's just the rough idea. Let me say one word about the C1 topology. Why is the C1 topology so flexible? So a little story here. Those of us in dynamics, at least those of us coming out of, well, really out of the school that goes way back to, Berghoff and Hopf and so on, but those of us who come out of the Smale school are interested in questions of these types of generic questions, because of course you can't say something about every dynamical system. Otherwise it wouldn't be a very interesting class of things to study. So we try to isolate certain dynamical systems inside of a larger space using a topology, using the smooth topology, as smooth as we can, to say something about the systems. And some things in some smoothness classes we can say a lot. Or rather, for some questions, we can say something in all smoothness classes. For example, the Kupka-Smale theorem asserts that for a generic diffeomorphism in any smooth topology, all the periodic points of a fixed period are isolated and hyperbolic.